but they were always going to be great. And it has just been a real privilege in watching where she grew to and what she did. And I think even more importantly than just knowing her academic prowess, which is extensive, but also her finding balance and limits and constructing a life that I think will be rewarding and sustainable in wonderful, wonderful ways. Her next venture is quite daunting to me. It's something that I go, what? That she really is going to sit down and write a book on iron, and you'll see iron even sneaks in here. And I just am so excited for this opportunity because I had the privilege of reading Erica's physical chemistry homework, in which there is a clear and distinctive voice about how things are done and how things go about, and I just know that this is going to be a really neat perspective and wonderful venture, and just a wonderful place for her not only to voice kind of her passion for the science, but her passion for the world. And I just know she's going to do great things. So today we're going to kind of take a couple steps back to a project that you did a few years ago at Madison, and even then she goes off somewhere where she doesn't have all that much control of her project and she still sneaks in iron. So with no further ado, Erica.
So, like she mentioned, 2 years ago, I drove down to Madison, Wisconsin, and right off the bat, I started doing research in a lab under Thomas Brunel, and Rebecca Fernandez was my mentor. So, for the course of the summer in Madison, I investigated oxidation states of iron-containing enzymes, specifically thiol dioxygenases, and I used a special type of spectroscopy called magnetic circular dichroism. So I just threw a lot of words at you, and they're all very exciting and wonderful words, and I promise we'll really get into what they mean. But before we do that, I'd like to give you the broader context of why this research was being done in the first place. So thiol molecules are sulfur-containing molecules. They occur naturally in the body. And there are correlative studies where if we have a high concentration of these thiol molecules, there are links to epileptic activity, Alzheimer's disease, and dementia. Also naturally occurring in the body are these things called thiol dioxygenases, which are enzymes. And what they do is they convert these thiol molecules into something usable, therefore decreasing thiol molecule buildup in the brain. So if we understand how these thiol molecules convert how these thiol dioxygenases convert thiol molecules into something usable, then we can potentially counteract symptoms of these neurodegenerative diseases. So what is an enzyme? Well, simply put, enzymes are biologic catalysts. We have a starting material and we want to go to create our product. And we need to understand how energy is associated with the reaction progress as we go from our starting material to our product. So if we think of our starting material here and our product here, in order to create the product, we need to go through a transitional state which requires a certain amount of activation energy. If we introduce an enzyme, well, we can think about enzymes as a lock and key model. So for every enzyme, there is a specific substrate that can be catalyzed to create a product. So let's say that we have now a substrate specific for this enzyme instead of just a starting material. Well, it's going to fit like a lock in a key, or a key in a lock. It will catalyze the reaction to then form the product. And in doing so, we decrease the activation energy required to create the product. So the takeaway here is that enzymes lower the activation energy required to create products. And what's important to note here is that these are reactions that are occurring in our body right now. And we could change the efficiency of a reaction over in the organic lab by altering pressure, temperature, pH, how much we're stirring it. But those are things that the body can't do. If we increase pressure, if we increase temperature, that's problematic and we could, die. So what enzymes do is they are able to control how the substrate binds to it and then lower the activation energy required to create a product and overall create more efficient reactions. So what's important to note is that metals can act as the active site in enzymes. And there are a lot of enzymes out there that have magnesium, zinc, or cobalt that act as this place where the binding occurs and where catalysis occurs within the enzyme. But I care about iron. So iron is a common active site within enzymes. Let me tell you, there are so many enzymes out there that contain iron. So I'd like to talk about why iron is so special. Surprise, I have pictures of rocks. So iron is really, really abundant on Earth, and from a geologic perspective, that's awesome, it's abundant. And I have pictures here of banded iron formations from Ontario, Canada. And banded iron formations stopped forming about 1.85 billion years ago. And as we can see here, these are stromatolites, which are microbial fossils that are recorded within these layers of iron-rich materials. So I'm not saying that because we have fossils here that's potentially why we have iron in our body right now, but iron is special for a lot of other reasons, which I'm about to explain. But because it was abundant, potentially the fact that it was dissolved in the oceans 1.85 billion years ago and earlier on, the proximity of microbial life to that iron, they could have evolved around the iron being there because it is very special. So we got a lot of iron, it's special because it's abundant. But like I said, it's special for other reasons. The first being that it's the most atomically compact and stable element on the periodic table of elements, which coincides with why it's so abundant. But I'd like to focus on these other two aspects. The first being that iron exists in two common oxidation states, iron 2+ and iron 3+. Iron is also a transitional metal, which means that it can take up to 6 different bonds and comfortably bond to 6 different things, which is really important in catalysis. So if we think about these last two things, why does that make iron special? Well, that means that it's very chemically versatile. So oxidation states we can think of as a transfer of electrons. We're all familiar with rust. Something in our life is rusted, probably something on a car, or we've come across a rusty nail on the sidewalk. And really what's happening here is we have iron in its ground state, and it can transfer either 2 or 3 electrons, either to oxygen or water, somewhere in its surrounding environment. And what's important is that it can exist as 2+ or 3+, which means it can comfortably donate 2 or 3 electrons. In terms of bonding coordination, if we look over here at our periodic table, right up here, this is the first row of the transition metals, and all of those metals have d orbitals, which look something like this. So what is this? Well, these are amazing. Let me tell you about it. Basically, what these pictures represent is the probability of where electrons can exist around the nucleus of an atom that has d orbitals. And iron has d orbitals, 1, 2, 3, 4, 5. So basically, when we have orbitals overlapping, that's when we get a bond to form. So around an iron nucleus, it can take up to 6 bonds because it has these d orbitals. So as I mentioned before, there are a lot of enzymes out there that have iron as the active site. And the most common is iron contained within a porphyrin ring, which is called heme. So if we think about this three-dimensionally, it's a very flat structure where we have these 4 nitrogens surrounded by a bunch of conjugated carbons, and we have an iron that then has its 5th and 6th bonding coordination sites on either side. So this is a very common structure in a lot of enzymes, and these are just a few to list off, just to give you a sense of how many heme enzymes there are out there. And just for further context, hemoglobin, which is why oxygen can flow through our blood, it's not an enzyme, but it also has this structure. So, going off of that, we know so much about heme. We really understand the mechanism by which substrate can convert to product because there are so many heme enzymes and because it's a part of blood, which is something that we need to understand. So my thiol dioxygenases, the enzymes that I worked with, well, they also have an iron center, but they look absolutely nothing like this heme structure. So we can see here we have our iron, and then we have 3 histidines, which are amino acids. And then there are 2 other sites where the substrate will bind. So in this case, we have iron binding only to 5 things, which is still okay, it's still comfortable with that, but it's completely different structurally. And because of this, we really don't understand the mechanism by which these thiol dioxygenases will catalyze the substrate into product. What we do know about thiol dioxygenases is what they catalyze. So again, going back to this thiol group, we don't want this to build up because it can lead to neurodegenerative diseases. But if we have that combined with oxygen, the thiol dioxygenase will catalyze it into a sulfonic acid, and in doing so, this sulfur becomes oxidized. And it is the oxidation of this sulfur that makes it biologically usable and available within our body. So there are 3 thiol dioxygenases that we know of. They've been named based on what substrate they are associated with, if we think back to this lock and key model. So we have cysteine dioxygenase, CDO, cysteamine dioxygenase, and 3-mercaptopropanoate dioxygenase, which I'll refer to as MDO. So these 3, we know they have a center or an activation site that looks something like this. And here is a picture from the protein data bank of cysteine dioxygenase, which was the first of these thiol dioxygenases to be crystallized. So this is how we know and can predict what they all look like. But what's important here is all of these have been named based on what substrate they catalyze into product, but we have absolutely no idea the mechanism by which they do so. So throughout the course of my summer at Madison, I spent a lot of time with 3-mercaptopropanoate dioxygenase and really tried to understand the mechanism by which this enzyme converted substrate to product. So the specific reaction is going from 3-mercaptopropanoic acid. Again, we have our oxygen, and then here again we have our oxidized sulfur. And the real question is, how the heck does it do this? We're going to find out. Okay, so this is the enzyme. This is just one enzyme that has been crystallized again through the protein data bank. And there's a lot going on here, but really I care about this iron center. So if we look closely here, here we have our iron, we have our 3 histidines, again to remind you what it looks like. And what we're trying to understand is how this thiol group and this oxygen will bind here at this oxygen. But I want to call your attention to this molecule here, which is called histidine, and also this tyrosine. So these yellow lines indicate that they're maybe interacting with the iron. They're not bonding. There's no real electron or orbital overlap, but they could be influencing how this iron is bonding to the substrate and oxygen when catalysis is occurring. So to understand how the lock and key of this substrate and our enzyme work, what we focused on were these 2 amino acids and how they associate with the iron. So what we did, actually I didn't do this, a lab in Texas did this, they expressed different variants focusing on these 2 amino acids. And this histidine was replaced by an asparagine, and in doing so we're trying to understand how the nitrogen on this histidine could influence the iron. And then they also changed this tyrosine into a phenylalanine, and this was for the purpose of trying to understand how this hydroxyl group could potentially influence the iron center. So these variants were expressed in a lab. I had nothing to do with this. But what I did was spectroscopy. So what is spectroscopy? Simply put, it's measuring changes in light upon interacting with matter. So if we have some form of initial light, we send it through our sample, the light then becomes altered. We can measure the change from here to here, and we can gauge some information about what is going on in our sample. So I used this type of spectroscopy called magnetic circular dichroism spectroscopy. I'm going to talk to you about what that means. So again, we're measuring changes in light after it has been passed through our sample. And for those of you who are thinking about Thayer's law right now, that's not at all what's happening. We are not measuring absorption of light or emission of light. What we are measuring is something very different. So let's imagine it's a sunny day. I think it's sunny outside. We have light propagating from the sun in all different directions. There's no orientation really to these propagating waves. And here we are, that's me getting sunburned. I have my polarized sunglasses on. So what's happening when I wear these polarized sunglasses is I'm directing the orientation of which the light goes through the sunglasses and therefore what I'm seeing. So when you wear these, then you don't get a headache because you're basically orienting what direction the light is propagating. So for magnetic circular dichroism, the spectroscopy that I was using, it's kind of similar to this because we're changing the orientation of light, but this is plain polarized light. I was using circularly polarized light. So if we look at this image, we have this blue spiral that's coming off, and that is being created because we're adding a magnetic field and an electric field. So I know it's hard to see, but this red line that's essentially parallel, that is equated to the electric field. And then we have the magnetic field, which is directly perpendicular to it. And when we have those two fields added together in a certain manner that is polarized, then we get circularly polarized electromagnetic radiation, or light. So if you think about looking straight down this spiraling circle, we have this circle where we have our green vector and our red vector that add to get this blue vector. And when we pass it through our sample, it alters basically how circular the light is. So really what we're measuring with circular dichroism is the angle from which our sample has altered the light. So we're basically measuring how ellipsoidal the light has become. So to take a step back, we can think about our light being first a circle, after we pass it through our sample, it then becomes an ellipsoid. So here is the instrument that I came to love and hate because I worked with it so many hours. Here is JASCO. This is our laser. So this is our light source, which creates the circularly polarized light. We put our sample in our sample chamber, and we cooled it down to 4 Kelvin. So just for frame of reference, that's negative 430 degrees Fahrenheit. And then over here, we have our detector for measuring how ellipsoidal our light has become. So I've been talking about magnetic circular dichroism, but I haven't really mentioned anything about magnetism yet. So most of you are probably familiar with something called ferromagnetism, which are all the magnets that you have on your fridge. And really what this is a bunch of iron atoms put together that create a magnet. But this is not the kind of magnetism that I was using at all. I was using a kind of magnetism called paramagnetism. And basically what this means is that if we have a paramagnetic material, if we induce an external magnetic field, then it becomes weakly attracted to that magnetic field. So if we think about a bunch of electrons in our paramagnetic material under no magnetic field, they're oriented in a bunch of different ways. But then if we apply something like a very strong magnetic field, then they all become oriented. And I want you to think about these electrons as lone pair, or as a single electron as a pair, as opposed to electrons that are paired. So iron, okay, so then what's important is that we have this iron in the middle of our huge enzyme, which means that if we have an enzyme and an enzyme and an enzyme, there are ions in all of those, but none of those ions can talk to each other. They can't become ferromagnetic. But again, going back to our d orbitals here, if you remember it, these are the probabilities of where electrons can exist around the iron atom. If we think about specifically iron and what our d orbitals look like, well, in the ground state, this is our electron configuration. So we have 5 d orbitals and 1, 2, 3, 4, 5 lines, and we fill them up with electrons. So here in the ground state, iron has 2 lone electrons. They are not paired, which means that iron on its own in the middle of this enzyme is indeed paramagnetic. So we know iron in its ground state is paramagnetic. We have 2 lone electrons. But what's really special about iron in this case is that iron 2+ and iron 3+ are also paramagnetic. They also have electrons that are not paired. And this is specific to the coordination of iron within the enzyme, and also the fact that the iron atoms are isolated from one another. So that's very special. Okay, keep that in the back of your mind. So I've been going on about the fact that it's paramagnetic, but why does that matter in the broad sense of using magnetic circular dichroism? Well, if we just have circularly polarized light and we send it through a sample and measure some form of ellipticity from our sample, what we're looking at is this entire thing. And there are a lot of other paramagnetic substances within our atom, but basically if we don't have a magnetic field, we're getting signal for this entire enzyme. And let me tell you, for 200 molecules, when we're just considering amino acids, that would be a very difficult spectra to try and understand. So, because we know that iron is paramagnetic and it's isolated from a bunch of other atoms, if, let's say, we introduce a magnetic field that is 7,000 times the strength of a typical fridge magnet, what we can do is we can tease out specifically a signal from the iron because we have a magnetic field that is aligning those irons in a specific way. So when we send our circularly polarized light through our sample with a magnet around it, then we're getting a signal that's simply just because of the iron atoms. So, because iron is paramagnetic, the signal of circularly polarized light when passed through the sample can be attributed to just simply the iron atoms. So this is very special because it's very specific to this particular enzyme in that both ground state iron, iron 2+, and iron 3+ are all paramagnetic. So that when we introduce the magnetic field, we can tease out what different peaks are relative to just the ions and not the rest of the molecule. So this is what a spectra looks like from an MCD spectrometer. And I'd like to go through how we can figure out what anything means based on these spectra. So on the x-axis, we have our wave number, which is this symbol in the red. And just for ease, it's proportional to energy. So as we're going up in wave number, we are also going up in energy. On the y-axis, we have ellipticity, which again is the degrees away from being a circle after we pass through the sample. We're also looking at different temperatures. In this particular figure, we tested it at 4 Kelvin and also 25 Kelvin. And that's just to try and understand whether or not temperature is important. Turns out it isn't. So then what's important here is that these different peaks can roughly be associated with different oxidation states of iron. That's very exciting. Okay, so let's look at what I did overall. Let's take a step back and see what I did for my research. At a collaborative lab in Texas, they expressed the variant and wild-type enzymes that I mentioned, where we replaced a histidine with an asparagine and then a tyrosine with a phenylalanine. I got those samples and I combined both the wild-type enzymes and also the variant enzymes with a bunch of different substrates to see whether or not something would bind. And then I used magnetic circular dichroism to try and understand whether things would bind or not and how the iron was interacting with these different variant molecules, the different variant expressions. Okay, so this is one of the spectra that I collected while I was at Madison, and I'd like to break it down. Okay, so this top spectra is the variant in which we replaced this tyrosine with a phenylalanine, again trying to understand whether or not this oxygen has anything to do with the oxidation state of iron. This spectra is relative to the histidine, so we replaced the histidine with an asparagine to try and understand whether or not this nitrogen has anything to do with the iron. And then down here, this is just when there are no changes to amino acids. So I'll call your attention to this specific peak. So if you look here, I promise there's a little peak right here. It's kind of hard to see with this line. But what we can see here is that, oops, oh no, okay. What we can see here is that this peak has been downshifted in energy as compared to this peak and this peak. So the Y159F variant has been downshifted. But what does this mean? Well, what we concluded is that because this particular spectrum does not have the hydroxyl group present, we can conclude that this hydroxyl group does in fact influence the oxidation state of the iron atom. And this is exciting because really what we're doing is we're saying, okay, this hydroxyl group on this particular amino acid really influences how the substrate could bind and will bind to the iron. So we're really getting at understanding in depth the mechanism by which substrate binds to enzyme. I also, with the other variant, so the Y157N, so this is, again, where we replace the histidine with the asparagine, I added different substrates to this enzyme to try and understand whether the oxidation state of iron would change. So in this spectra, I just added D-threonine, and then here I added D-threonine with 3-MPa, which is the known substrate of 3-mercaptopropanoate dioxygenase. So again, I'll draw a line here and call your attention to this peak down here. It's lower in energy for the as isolated enzyme as opposed to when I've added any number of substrates. So what we can conclude from this is that the D-threonine has an influence on the oxidation state of iron in this particular variant, but the 3-MPa does not. And this is weird because this particular enzyme was named based on the lock and key model. We know that MDO binds to 3-MPa, and that's why it was named in the first place. But the fact that we're not having any difference between the D-threonine with 3-MPa and just D-threonine, this implies that this variant, or the histidine here, so probably the nitrogen, influences substrate specificity. So it does influence basically whether 3-MPa can bind or D-threonine. So, some concluding remarks. The paramagnetic iron active site of MDO allows us to use magnetic circular dichroism spectroscopy. It all comes back to iron. The hydroxyl group on this tyrosine influences the oxidation state of the iron active site. And then this histidine influences what substrates can bind to the iron. So we're really getting at understanding how these little amino acid residues in proximity to the iron influence the lock and key model of 3-mercaptopropanoic dioxygenase binding with its substrate. And we can conclude that these two amino acids do have an influence to some effect. Okay. So then future work. Unfortunately, the variants that I were working with all had impurities, heme impurities, ironically enough. And so in the future, expressing more of the wild type variants to try and understand how they bind to the different substrates and just get a better idea of what's happening there. There was a dissertation that just came out last year from the lab who created the variant enzymes, looking at electron paramagnetic resonance spectroscopy of the thiol dioxygenases and MCD in particular. But I would also be interested in looking at MOS virus spectroscopy of these thiol dioxygenases, because MOS virus spectroscopy is specific to looking at different iron isotopes. So we could potentially gauge a lot about the iron center of these enzymes. So another part of my lab group, so there's the spectroscopy part of the Brunel group, but they also do a lot of computations. So they often pair those two to try and understand mechanisms more. So I would be interested to use density functional theory and then quantum mechanics, molecular mechanics, computational techniques to then pair with this spectra that I have, and then hopefully better understand the mechanism of how substrate binds to MDO. I have a lot of people to thank. So I did this research at the University of Wisconsin-Madison. Rebecca Fernandez, first and foremost, who held my hand through the entire summer and was such an amazing spirit. Thomas Brunold, who was my PI. Elizabeth Greenlaw and Mickey were both part of my lab group as well and were an amazing help to me. Steph, I used her lab notebook so much because she had just graduated and I followed most of her procedures. Brad Pierce is the PI of the lab that created all the variants for me. I used Brian Fox's lab a lot when I was doing another project at Madison similar to this one. And then Wyatt Smith, who has since graduated, but was also in Madison with me 2 summers ago and was such an amazing support and really helped me get through the summer. And then Dr. Andrew Greenberg, who coordinated this entire REU organization that I was a part of. And I got funding through NSF and MRSEC. So then, I also have a bunch of people from Lawrence to thank. Graham Sazima, who can't be here, who is my research advisor for this project, Dr. Deanna Donahue, who has been such an inspiration to me and has been such a wonderful academic advisor for me, Allison Fleshman, who also can't be here, who has inspired me to go on and study physical chemistry in the future and also helped me understand magnetic circuit dichroism and spectroscopy. Dave and Stefan, Dave for running this class and also being an inspiration for biochemistry. And Stefan, thank you also for inspiring me to like organic chemistry. All my chemistry compatriots, you know who you are. Thank you for all the late nights in that computer lab downstairs. My parents, John and Patty Craddock, who so wonderfully could come and who have been such an inspiration to me in my entire life. All of my friends who supported me along the way, I love you all. And then I also had the privilege of presenting this research at the ACS Orlando meeting at the beginning of April, so I want to acknowledge that Sherman Fairchild funded me to do that. Thank you. Questions? Yeah.
Okay, so the magnetic circular dichroism, I'm just curious, like, if you know of any other techniques that that's used for, and it's like only you can only apply it to iron, or if it works with other atoms too?
It works for, so I know this type of spectroscopy is mostly used for understanding enzymes and like the chirality of active sites, but pretty much if you have anything that's paramagnetic, I know in my lab we also did stuff with cobalt. So whatever the active site is, as long as it's paramagnetic, you would get a signature. Yeah.
Do you guys have any hypotheses about how the hydroxyl group would affect the oxidation state?
So yes, but it's really complicated and it involves looking at the different geometries of the active site. We can talk about the splitting d-orbital spin diagram later if you want to, but I don't want to get into it right now because it would take a while.
Other questions? Let's thank our speaker again then. "15-minute bathroom and food break, and then Sam will be up. I'm introducing you. What are you doing? What am I doing?
Yeah.
For what do you want? I am at least for a year or two just going to work in